Last time we started talking about more specific tests than the one that we had done last Thursday. So last Thursday we had found a test that allowed us to determine whether a given mean was larger than a number, smaller than a given number, or different than a number. On Tuesday, we created a test that also allowed us to study proportions. And then I introduced a test that allows us to compare two different samples, right? So we said the test is applied for two independent samples, and it allows us to test for a difference between those two samples. The example that we had for that was that a group of statistics students were asked to measure their middle fingers, and we want to determine whether there's a significant difference in the lengths of middle fingers between women and men, right? So that's what we're doing. We're trying to test for a difference between women and men. The results are summarized below for female and male students. So that means we have two samples, a sample of females, a sample of males. So sample A and sample B, and for each one of them we have the sample average, we have the sample standard deviation, and we have the sample size. And what we want to determine is if there's a difference in the means of middle fingers for women and for men. So what we said is we're going to start with the assumption that there is no difference, so that they're the same. So that would mean that the mean length of middle fingers for men is the same as the mean length of middle fingers for women. But because our test was formulated in terms of the difference between the means, we have to rewrite this condition as a condition on the difference between the means. Then we have the alternative hypothesis, which is that they're different, in which case, again, we have to reformulate this in terms of the difference between the means, because that's how my test is written. The second thing was to find the level of significance, which in this case was my mistake. It wasn't specified, and I think I said the level of significance should be 0.05. This is what I'm going to do today, but of course, it was the same for any other level of significance. It's just a matter of which column you're looking at in your table. And then in the third step, we actually have to do the test, right? So we have to figure out what test to use. We have to find the critical value, we have to find the test statistic, and then we have to conclude, right? So always the same 4 steps. Now, the first thing here is to realize that because we have 2 samples, we're doing a 2-sample test for means or a 2-sample t-test. The second thing that we have to do is to find the critical values. And in the same way as usual, this is always the same thing. We have the critical values are the values that separate what's normal from what's unusual, what's extreme, right? So that means that here we're going to have, for a given distribution, we're trying to test for whether my means are different than 0 or equal to 0, right? So that means we're not testing to see if the mean is larger than 0. We're not testing to see if the mean is smaller than 0. The difference is smaller than 0. We're testing to see if they're different than 0. So that means that I will have enough evidence to contradict my original hypothesis, which was that it is equal to 0, if either the difference is too large, so too different than 0 on the positive side, or too small in the sense that it's large and negative, right? So it's further away from 0, but on the negative side. So that means that if I have either a result that is too large and negative or too large and positive, then I will have to reject my null hypothesis. I will have enough evidence to contradict my original hypothesis, right? So I'll have to go to the t-table and look for the value that separates the extreme on both sides from the middle usual information, right? Now, because here we're chopping information from the top and the bottom, that means that we have to look at the row that says 2 tails. And so it's a 2-tailed test because we're looking for significance both on the positive side or the negative side. Can I see a show of hands for those of you who understand this? All right, not bad. Again, I repeat this a lot, but please, please, please do it. If you do have a question, just interrupt me either through the chat or with your by turning your mic on and asking me questions there. Okay, so what I have is that I'm trying to find a value that separates the extreme 5%, because this is 5% over here, from the middle 95%. And I have to remember that my tail is a two-tailed test. Now, because I have two samples in this case, I'm going to have to determine the degrees of freedom through the formula that is given in the test, right? So we said the degrees of freedom, the row that we're going to look at in the t-table is given by sample size for the first sample plus sample size for the second sample minus 2. And so in this case, we have that the degrees of freedom are going to be sample size for the first sample, that's 16, plus sample size for the second sample, which is 11, minus 2. And this gives me 27 minus 2, which is 25. Okay, so we have level of significance, number of tails of our test, and the number of degrees of freedom. With this in hand, I can now go to my t-table and use the information that we just came up with. So we have a t-test that has to have two tails, right? So two tails means I'm going to be looking at this over here. And I know that it's 5%. So I look for 5% in the two-tailed part of the table. And then I found that the degrees of freedom were 25. And so I'm going to get 2.060, right? And so this is going to be my critical value. So again, what we need to do is determine if we have a one-tailed test, so if we're just looking at larger than or smaller than, or if we have a two-tailed test, so that means just looking at difference. And in this case, we're just looking for whether the length in the middle fingers is different between both sexes. And now we look at the at 0.05, the level of significance on that two-tailed row over here. And the row that we're going to look at corresponds to the degrees of freedom, which is 25. So that means that I get 2.060, and I can go back now to my problem with that value. So that means I have 2.060 here, but I also have negative 2.060, right? This was a two-tailed test, which means that my result can be considered extreme if the difference is either very large or very large and negative. So that means it's larger than 2.060, or if it's smaller than negative 2.060. Okay? Can I see a show of hands for those of you who understand this?
Miss, may you go over how to find that on the T-chart again?
Sure. So important parts to remember when I go to the t-table is I have my level of significance. I have the fact that this is a two-tailed test, which means that I'm looking at both larger than or smaller than. And I have the degrees of freedom, which is 25. Okay. So if I go to the table, I start by finding two tails. So that means this number over here, I'm going to go to two tails. I look for the level of significance that I'm using in this case, which is 0.05 or 5%. And then I look at the row, which is the number of degrees of freedom, right? So we found that in our case, the number of degrees of freedom was 25. And so I just have to look at the intersection between this column and this row. Okay, and that for us is 2.060.
All right, thank you.
All right. And so now I have those values, and I'll conclude that my result is too extreme to be explained by samples that don't have equal means if my result is either too large, so if the difference is too large, or if the difference is too large but on the opposite side. So that means if either males have middle fingers that are a lot larger than females' middle fingers, or if females have middle fingers that are a lot larger than males' middle fingers. Okay? So that is going to be determined by the statistic that we have to evaluate at step C over here. So for step C, we have to find the test statistic. And the test statistic is not that difficult to find once you have found the horrible thing that is the shared standard deviation. So what we have is that T is going to be equal to X bar for the first sample minus X bar for the second sample minus the difference, or the comparison value, but in this case, that comparison value was 0. We were just checking if the difference between them is different than 0 or not. So this over here. This number over
Wait,
here,
Miss,
the 0. Yeah.
what is the 0, like what's the 0, or like what does it represent?
The 0 is just the difference that you're comparing this to. So this 0 comes from this 0. You're just checking if the difference between the means is equal to 0 or not.
Okay, thank you.
Yeah. And then you can divide this by SAB, which is honestly the hardest part of the problem, is finding this or being able to plug this into your calculator. If you do that correctly, then you're good to go. So here we go. We have that SAB. This is an estimator of the shared standard deviation between the samples. So it has to be a combination of the standard deviations for each one of the samples. And so I'm going to have to plug all of this into my calculator. First, sample size for the first sample minus 1, so that's 15, times SA squared, so standard deviation for the first sample, which is 6.22, squared, plus sample size for the second sample, which is 11 minus 1, so that's 10, times standard deviation for the second sample, which is 6.01, that thing squared. The whole thing divided by 16 plus 11 minus 2. And then this whole thing multiplied by 1 over 16 plus 1 over 11. And then close the square root of all of that.
Why on the numerator is it 15 and 10, but then on the denominator is it 16 and 11?
Yes, so it's from the formula. I'm talking about the formula exclusively. I can't change. Okay, well, I don't know what's going on. Okay, so over here in the formula, I have NA minus 1. That just means the sample size minus 1. And that's just because in the original formulation, like the person that did all the math in order to verify that this is the case, we have to consider the degrees of freedom for the first sample and the degrees of freedom for the second sample. So it should be just scaled with respect to that. But the reason here you don't have to worry about it too much. The only thing that's really for you to remember is that here you have NA minus 1 and here you have NB minus 1. Okay?
Okay,
Yeah.
but like for when we're using a t-table, right, or when the sample size is under 30, it's already n minus 1, right? So in this case is like n minus 1 minus 1.
Yes, so in this case it's
Okay.
n minus 1 and n minus 1 because you have 2 samples. So for each of them you have 1 degree of freedom less than the sample size, which is why you end up.
No, like I mean, because for the sample size already we have to do n minus 1, right? Because the sample size is under 30, right?
Mm-hmm.
And then do we have to do it again for the numerator? Do we have to do minus 1 again? So really it's like minus 2?
No, you just follow the, like basically you just follow the formula that is given based on the sample size that you have.
Okay.
Second?
Yep.
Okay. So after plugging all of this in, again, I suggest that you try to do this on your own and you make sure that this is right. But I already did the calculation for you. This gives square root of 5.78 which gives approximately 2.40. Okay, so all of that is just to get the denominator, and that's 2.40 in this case. Okay, so in this case, now we have 2.40. I can plug in the value of x bar A, x bar B, and SAB now because I have all of those values. So XA, so the sample average length of the middle fingers for males is 109.94 minus 98.55 divided by SAB, which is 2.40. And this gives me 4.74. Okay, and so the last step over here is just to conclude. And to conclude, I just have to check whether my result, the value of t that I have over here, is in the usual region or in the extreme region. 4.74 is way larger than 2.060, is maybe like around here. And so that means that I can reject the null hypothesis. When I say I can reject the null hypothesis, what I'm saying is really, okay, there seems to be enough evidence to contradict the original assumption that the means were equal. So the means should be different. Right? So I have enough evidence using a level of significance of 0.05 to say that the average length, length of middle fingers is different for men and women.
So what does the score in this case across represent? Like across, like the usual would be like the expected value, but then on the tail ends when it's outside, what does that represent?
Okay, so whatever, do you mean like here?
Yeah.
Okay, so what that means is what is a different enough difference that I will conclude that there is a difference.
Oh, okay.
Does that make sense?
Mm-hmm.
Yeah, so like how much of a difference should I have between my samples in order to conclude that that's not just by chance and actually because there isn't a difference from the original populations.
Okay.
Yeah. All right, so everybody lower your hand and please only put it back up once you're done writing. Okay, so right now what we're going to do is to start talking about measuring association, which becomes important to us because so far we have started we've talked a lot about how to describe single variables, right? So we already know how to describe single variables. how to plot and quantify single numerical variables. So what I mean by plot and quantify is that well, we know how to plot, how to sketch numerical variables. We know that we can draw these by using histograms or by using box plots. And we know how to quantify them, so how to describe them with numbers by just looking at either the mean, the standard deviation. We also had medians, we had modes, and so on. We had range, a bunch of measures of variability and center. And we were able even to determine if our results, our values for those means and so on, were statistically significant by doing hypothesis tests. And so this is what we've done so far, most of what we've done this semester actually. And it's interesting, it's nice because it allows us to describe single data sets, but really what we are most interested in determining is whether there is a given relationship between two variables, right? So is it possible that one thing is affecting another, or that there is a given relation between two variables? That's something that we were interested about even at the beginning of the semester. But we had to start with something simple and then actually start working on solving this type of problem. So the next thing that we're going to do, we're going to try to look at today is how can we describe association between two variables. Okay, this is the main thing that we're going to be talking about today, which is how to describe association between two variables. Now, before I start talking about this, I'm going to divide this into two parts, one of which we have already covered. The first thing is how to plot association between two variables, and the second thing is how to actually quantify or measure association. Now, in this class, we already saw how to sketch two variables at the same time. If you remember, this was completely at the beginning of the semester, and what we did is something that we called scatter plots. Can I see a show of hands for those of you who remember what a scatter plot is? Okay, very good. Lots of hands up. I like it. So a scatter plot is, just something that looks, that looks something like this, right? So like you have some kind of data, and it has, it plots one of the variables on one of the axes and the other variable on the other axis, right? And each one of the points represents just a single observation, right? Where the coordinates are given by the first variable, like the x coordinate is given by the value in the first variable, and the y coordinate is given by the value in the second variable. Show of hands for those of you who remember this. Very good. All right, so what we're going to do today is really to focus on how to quantify those relationships and how to measure them. So the first thing I'm going to ask you to do is to think about if you can't, like two variables that you think are going to be associated. Are there any two variables that, at the top of your head, you think should be associated? And I'm going to go here from your examples, at least for this slide. You can answer in the chat or using your mic.
Miss, as in like what?
As in like anything. Two variables that you think are linked to one another.
Your grades and how much you study.
Grades and how much you study. Very nice example. So let's say time spent studying. And the grades. And what do you think the scatter plot is going to look like? For example, if I spend very little time studying, do you think I'm going to have very good grades or very low grades? This is one that should be natural to everyone.
Good grades.
If you spend a lot of time studying, you're going to get good or bad?
Good.
Okay. If you spend very little time studying, are you going to get good or bad grades?
Bad.
Bad. Now, that doesn't necessarily mean that everybody that spends few hours studying is going to get bad grades, right? Maybe somebody is going to get a little bit better grade. Maybe if I study a little bit more, I'm going to get something slightly higher, but maybe there's one person that's going to get still low results, maybe one that's going to get pretty good results, and so on and so forth, right? And so the results should look something like this, right? There might be somebody that spends a lot of time studying and still doesn't do that great, and so you're going to end up with a scatter plot that looks something like that. Now, so here this is time studying and grades. What's another pair of variables that could be correlated or associated? Anyone? Oh, there you go. Daily ingested calories and body weight. Okay, so we have calories and weight, right? And so this is daily, right? So this would be daily calories and weight. And then if you consume a lot of calories, then likely your weight is going to be high. And if you consume very few calories, maybe your weight is going to be low. But of course, this is not necessarily true for everyone in exactly the same measure. So you should also expect some variability here, right? So you're going to get something like that. Right, so this is something that can also be intuitive. Now, another option that was proposed was sleep and growth for children. So that could be true. So if you can try to measure how much a child is sleeping and then try to determine their growth rate during a certain amount of time. It's true. Now, what I want you to think about for the next example is something that would not be directly associated. So over here, for both of these cases, what we have is that if the number of daily calories, for example, increases, then the weight should also, that should be associated with an increase in weight. Right here, if the time studying has higher values, then the grades have higher values as well. Now, can you think of any two variables such that if one of the variables increases, then the other one decreases? Anyone?
Number of hours studied and quizzes failed.
Okay, hours studying and number of failed quizzes. I don't even know what this is. And quizzes failed. And so if we spend a lot of hours studying, then it's likely that we're going to have 0 quizzes failed. And if we spend very few hours studying, then it's likely that that number is going to be slightly higher, right? And so depending on the time that you spend studying, you're going to have something like this. Show of hands for those of you who understand how all of these are represented. All right, so before we keep going, we're going to talk about 2 variables in each one of these cases, and those variables are going to be labeled something different depending on whether we put it in the x-axis or the y-axis, and that choice is going to depend on whether we think x is the explanatory variable or whether we think that a variable is the dependent variable. Okay, now I'm going to emphasize a lot during this class that when we're talking about association, we're not necessarily going to be talking about causation. So we're not necessarily saying that one of them causes the other one, but often when we're studying relations between two variables, we are assuming from the get-go that one of them is the one that's explaining the second one, right? So for example, here, if we have two variables, time studying and grades, then we have reason to believe that time studying is going to be an explanatory factor for grades, right? And less so that the grades are going to be an explanatory factor for the time studying. Although it could be, right? So for example, we could think maybe we'll find that if we do a little bit further studying, then actually grades is the cause of the time studying and not backwards, right? So we're always presuming from the beginning that there's one variable that can explain the other one, that can account for variations in the other, but that is by no means causality. Okay, so we're not actually going to be showing causality in this section. Although we're going to say is, okay, assuming that this is the one that's explaining the other one, what can we say about the relationship? Okay, so just warning over here, there's no causation in our discussion for the day. All right. Do I have any questions? Okay, so we're going to go to the next example, which is a scatter plot that has already been plotted. So you have the following scatter plot, which shows for a certain number of people, 31 people, you have the number of years that they have studied after high school. So the x-axis shows the number of years studied after high school, and the y-axis shows the income. Okay, so the yearly income for these people. Okay, so this is after high school. And this is the income per year. All right, so the first thing I want to ask you is, for somebody that has studied 1 year after high school, what would you expect the income to be approximately? If you had to guess what the income of a person that studied 1 year after high school, based on this data, what would that income be? Anyone?
Like around 35,000.
Around 35,000, right? Because it looks like it's between maybe 29,000 and 40,000 with a couple of values over here. So maybe it's this value over here, right? So it's about 35,000 per year. Now, if somebody studies more, so more years, would we expect the salary to be higher or to be lower? Easy question.
Higher.
Higher, right? So we have that it's higher because, for example, we can think of the case where we have studied maybe 8 years, right? For 8 years, it looks like the average salary is going to be somewhere between 82 and 90,000, right? So that seems to be the value around here. Now, because of that, what we are looking at is what we call a positive trend, right? So the more we have in this variable, the more we're going to have in this variable as well, right? And so we talk about a positive association in this case. What's happening? Okay, everything's okay. Sharing it again. There you go. Yeah, we're all good. Okay. So this is what we have. And so we have that because the number of years over here is, so if we increase the number of years, then we're also going to have that the income is going to increase. So what we're saying here is essentially that there is a positive association because an increase in the X value corresponds to an increase in the Y value, okay? Does everybody understand this? Please raise your hand if you do. All right, okay. Now, so this is a positive association because we have that if the first variable increases, then the second variable increases as well. Now we're going to talk about the other possible case. In this case, the number of texts that somebody sends during class, yes, sent in class, during class time, and the average that they get for that given class. Right? And so if a person is sending very few texts, then they're going to have a percent average that is going to be more or less high. And if somebody sends a lot of texts, then they're going to have a percent average that is going to be fairly low, which means that the higher the number of texts sent during class, the lower the percent grade is going to be, right? In this case, we talk about a negative association. And we talk about a negative association because we have that. If the value for X increases, then the corresponding value for the second variable is going to decrease. It's going to decrease. Okay, and now the idea for us is going to be to determine, okay, do we have in general a negative association, a positive association, and then also is my association really high or is it very low? And so do I have a very strong association between the variables or is my association not that strong? So based on these two examples, I want you to look at this on the board over here. So I have both of the scatter plots. This is text versus percent grade, and here you have number of years after high school versus income. And I want to see, based on this, what do you think is similar between these two scatter plots? What do you think is similar between these two scatter plots?
They're pretty similar in terms of the strength of the association.
Okay, so the strength seems more or less similar, which means that we have more or less the same amount of variability from the association that we see, right? So for both of them, we see some kind of trend, and there's about the same amount of variability for both of them. Right? So a similar amount of variability. Now, how are they different? Okay, well, this one is an easy one. How are they different? They're different because they have just a different direction of the association, right? We said this one, if we increase in X, we increase in Y, whereas here, if we increase in X, we decrease in Y, right? So the direction of the association is different, right? And so what we're going to try to do for the next couple of slides is to determine, is there a measure that could tell me both how strong the association is and the direction of my association? If you're understanding everything, please raise your hand. All right, so I want you to look at these 8 scatter plots. We have 8 scatter plots in this case. And I want to ask you to group them in groups that make sense to you. So if you had to group them into groups, however many you think you need in order to place everyone in a single group, what groups would you choose, and what are the characteristics that make you put them in the same group? So I'll give you 1 minute to think about those groups, how you would separate them. So you can basically kind of like just create groups and then say, like, I don't know, in this one I'm going to put A, B, and C, or A, C, and D, or whatever it is. Okay, so what groups would you create if you wanted to place each one of them in a different group? And what would the characteristics of those groups be? Does everybody understand the question? And if so, please raise your hand. Okay, go ahead, 1 minute. All right, so who has an idea of what groups we could use in this case? Where's the chat? Oh, there you go. Okay, so Erin proposes A and H. Here, okay. A and H, so this one and this one, have a strong positive association. Then you have F and C, which have a strong negative association. And then you have G and D, which have no real association. What happens with E and B? Where do E and B fall? Based on this classification, what is the most appropriate group for each E and B? So they're weaker associations, right? And we don't really know what type. Okay, so that's one possible grouping. You would have A and H in the same one, right? Because they're both positive. Have G and D in the same one because there's no relation, and F and C both in the same one because they are strong and negative. And then E and B are weaker associations. That's a good grouping. Does anybody have an alternative? Did anybody come up with a different grouping for the terms?
I put B and G together and the D and E
B and G together and
together.
E
D
and
and E.
D and E.
Yeah.
Why did you do that?
Well, for B and G, I deem them as both weak and positive, and for D and E, I deem them both as weak and negative.
Okay, so that's good. Yeah, so then here you had like both strong and positive, that would be A and H. And then what Alex is saying is positive and weak would have been B and G, right? So this one and this one, which look like they're still going up, but there's really not that much of an association. And for D and E, they're both, again, kind of going down, but there's really not that much of an association. All right, so that was another possible grouping. That's also good. Now, so essentially one of them is saying, okay, the strong and positives, the other one, the strong and negatives, the other one, weak and positives, the other one's weak and negative. Now, Chloe has another version, A, C, F, and H. So A, C, F, and H, they're all the less scattered. And B, D, E, and G, so those are the more scattered. So that means, Chloe, I think what you did was just say, okay, all the strong ones in the same one, all the weak ones in the same one. That's perfectly fine as well. That just means that you essentially said A, H, and then C and F, you put them on the same group, and then you put all the weak ones in the same group. That's also pretty good. Did anybody group them in any other way? Okay, seeing no volunteers. I think this is good. So that means that you're looking at two important things in each one of the scatter plots. You're looking at how strong the association is, and you're looking at what the direction of the association is going to be. For the next part, the next thing that I'm going to ask you to do is, again, with A, B, C, D, E, F, G, and H, I'm going to ask you to order them in a way that you would in a line. So if you had to align them in some kind of progression, if you had to put them from the least something to the most something, or in some kind of natural progression, how would you organize these scatter plots? So how would you order them from the least something to the most something if you had to put them all in a line? Does everybody understand the question? Please raise your hand if you do. Okay, so you'll have maybe 1 minute, 1 minute and a half to think about that. And when I ask for answers, I just want a list of letters that has a reasonable order. So I'll just think about the list of letters, and then it's just one list. Okay, that's it. So how can you classify these in a natural progression from the least something to the most something? 1 minute and a half on the clock. Okay, so I see several alternatives. I think Alex Maniolaris and Erin had pretty much the same. That AFGC. Okay, HC. Okay, so that's the same as Alex's and Erin's, and then I have AHBG. Okay. Okay, so I have a lot of options. That's good. And then I had DECF GHA. Okay. So here's what I see in the options. So we have, I think one of the most common ones is to do A. So AF, HC, BE, and GD. So that means to first look at A and F, which are the strongest ones, right? So you have like the strongest one, positive, and then the strongest one, negative. Then you have HC, which is pretty strong, positive, pretty strong, negative. Then you have BE, which are more or less strong, positive, more or less strong, negative. And finally, you have GD, which is the one that's like, is it even positive and is it even negative, right? So it's just kind of like always positive, negative, positive, negative, positive, negative. It's just that for one of the cases it's positive and for one of the cases it's negative. That's right. And this is classifying them with respect to one main aspect, which is strength of the association. So you're going from the strongest association to the least strong association. But this has the problem that it doesn't really look like a continuum of options, right? Because you're always going plus and minus, plus and minus, plus and minus, plus and minus. And so even though it's right, and I get the intuition that you're doing, it's not really a continuum of possibilities. And so that's why I'm going to go with the other option that was given, and it was given in both ways, which is to say, okay, let's say that I want to start with the strongest association, okay, that I want to start with A. Then I know that F is the corresponding one, but it's kind of like the corresponding one completely on the opposite side, because this one is really, really strong and positive, F is really, really strong and negative. So what I can do is I can say, okay, well, if this is going to be the most something, this is going to be the most the other thing, right? And then the next one after A is going to be H. So it's going to be H like this, and that means that the corresponding one with C would be like that. And then you have, well, the next one that's the strongest one in the positives would be B, and the next one would be H. And afterward, you would have D. Okay, I'm not going to do that. Then you would have E over here and D. Yeah. Right? And so in this case, you would start from the strongest and positive, then more or less strong and positive, then kind of positive and not really strong, then to is it even positive, then is it even negative, more or less strong and negative, pretty strong and negative, and really strong and negative, right? The actual way that we're going to do this in the class is actually backwards from this. So we're going to always start with the negative and end up with the positive to have something that looks like this, right? So the order that I was going for, in this case, just think about it as a continuum, was F, which was the strongest and negative, C, E, D, G, B, H, and A. Okay? So the idea is that whatever's in the middle over here is the thing that really has basically no relation. Then we have that everything that's before this is negative, a negative relation. And everything that's on this side is a positive relation. Now this should make it a little bit more clear why I chose to start F, C, E, D and not A, H, B, G. And it's because I would like the positive to be on the right and the negative to be on the left, as all math has ever been before. Okay? Then this seems to be almost perfect as a relation. So that means that the very end over here should be a perfect relation. And the very end over here should be a perfect relation, but in the positive side. All right. And so the measure that I'm going to create to describe the association between two variables is going to tell me that if there's no relation, the number is going to be, well, 0, because there's really no relation between the variables. So if I have no relation, then there's nothing, there's zero association. If the relation between my variables is perfect, then I'm going to have all of it, which in math is usually 1. And so I'm going to go from 0 to 1. And every value in between is going to be a measure of how strong the association is, right? So the closer I am to 1, the closer my association is to perfect, and the closer I am to 0, the closer I am to not having an association. And then on the other side, I'm going to have exactly the same type of reasoning, but I'm going to have something that is negative. So I'm going to have -1. Does everybody understand this? Please raise your hand if you do. All right, so this is exactly how we're going to define our measure for association, with the caveat, which I'm going to repeat a lot of times, that this only works for linear associations, right? So you can see that here we say perfect association. That means that this is almost a line, right? Same thing on the other side. This is perfect association, which means that this is almost a line, but with that positive number. So that means we're going to have that this is only for linear association. All right, do I have any questions, or is this okay for everybody? Seems okay. All right, so then I'm going to define the actual number that we have for the measure of this, which is called Pearson's R, or Pearson's correlation coefficient. Pearson's correlation coefficient, which is denoted by the letter R, is a measure of association between two variables. And the advantage of Pearson's correlation coefficient is twofold. It's that it actually expresses two properties of the association between the variables. So it expresses, first, the strength of the association, which goes from 0, which is no association, to 1, which is perfect association. And it also describes the direction of the association. So this can be positive if the function is going up, or it can be negative if it's going. And so that means this can be positive if we have something that's going up, or negative if we have something that's going down. So we're not going to go too much into how this is computed. I'm going to give the formula in a second, but I do want to express, to just speak about how it's obtained, so how we get it, just so that we understand the logic and why it only works with linear cases. So suppose that you have these, okay? You have a very strong negative linear association and a more or less strong but still pretty weak positive linear association. Okay, so this should be strong. So this should be, sorry, more or less strong. More or less strong and positive, whereas this one is strong and negative. So, can I see a show of hands for those of you who are done writing or okay with this so far? All right, okay. So if you think about the variables that we have here, we have two variables, one is x, one is y, each of which expresses something. So maybe we can go to the number of hours studying and the grade, okay, just for the sake of the example. Now, here we're displaying both of the variables at the same time, but in reality, we could also just describe the number of hours studying and the number of, and the grade for the class. So for example, if I had a class of 30 students, I could determine the average number of hours studied in the class, so the average number of hours that a student in my class is going to study, and I could find the average grade in my class. Right, so this is just by looking at the data sets one by one, and not at their length, but at each one of the data sets on their own. If this is the case, then I could sketch a line like this. And so every dot that is on the right of this line are all the students that spent more time than average studying, and all the ones on the left over here are the students that spent less time than average studying. Does everybody understand that? Please raise your hand if you do. So if you're on the right over here, this is more than average, and on the left, this is less than average. Do I have any questions about this? Is there anyone that has a question about that? Okay, then I can do the same thing for the grade, right? So the grade tells me, this is my average grade for the class, and any student that is above here, so like all of these dots that are above that line are the students that got a grade above average, and all the students that are below here are the students that got a grade below average, right? So above average and below average. So what the correlation coefficient, the number R, does is that it counts, it basically counts the number of points that are here and here. Okay, so these two quadrants with respect to the line, so these, like we're basically dividing our plane into 4 pieces. These are something that we consider to be positive, because if you're either above and above, so plus and plus gives you plus, or if you're below and below, so minus and minus gives you plus, then you're going to be in each one of these, whereas these are the negative sides. Okay, so we always have positive, positive, negative, and negative. What the correlation coefficient is doing is essentially counting the number of points that is in each one of these quadrants. And so here we have most of them are in the positive quadrant and most of them are in the positive quadrant. So if you add them, you have a bunch of numbers that add up to a positive number. But then because you still have some that are negative, you're going to have something that is positive but not quite equal to 1. If we think instead about the second example over here, let's say my average in y is going to be more or less here. My average in x seems like it's going to be here. And so here, again, I have plus and minus and minus. But here, most of my dots are going to be in the sides that correspond to minuses. Okay, so that means that a strong value in x is associated with a low value in y, and so plus and minus gives minus, or minus and plus gives minus, right? So we're going to have minus and minus over here, and so that's why my correlation coefficient r is going to be negative, whereas here my correlation coefficient r is going to be positive. Okay? So the idea is really that the correlation coefficient is looking at whether the x values are, so whether being above average in the x value is associated with being above average in the y value as well, right? So here, for example, values that are larger than average in the x value or have a tendency to also be higher than average in the y value, whereas here, values that are higher than average in x have a tendency to be lower than average in y, right? Whereas here we have values that are lower than average in x have a tendency to be higher than average in y. And I see a show of hands for those of you who understand this. Okay, so this is really just to emphasize on the fact that Pearson's correlation coefficient is just measuring, you know, whether you have a tendency to be above average on both or above average on one but not the other one. So let me go to the next slide. What we have is that, and here I'm going to emphasize on this again, the correlation coefficient can only pick up, so it can only pick up linear relations. So only works for linear association. Okay, so imagine that you have something like this. Okay, so you have something that is associated, and initially it's going up, but then as you keep going for high values in x, this starts going back down again. This is a classic example of when the correlation coefficient does not pick up a relation. So it should be pretty clear from the graph that there is an association between x and y, right? So it's pretty clear that you can predict y based on the value of x. There is an association between them. The only thing is that this association is not linear, right? Because you don't have just a line, you have something that looks more or less like this. For those of you who remember, this is called a parabola, right? So this is a nonlinear, this is a quadratic expression, not a linear expression. Now, if I try to think about whether something is above average or below average, I'm going to have maybe the average in y is going to be somewhere here, and the average in x is going to be somewhere around here. And so I'm going to have pretty much as many points in the positive sides as I have points in the negative sides. And so that means that I'm going to end up with having as much plus as I have minus. And so I'm going to end up subtracting a bunch of things, and I'm going to get a value for the correlation coefficient that is going to be approximately equal to 0. Right, and so that's just because the association here isn't linear. So I can't say, oh, if you're above average here, you're going to be above average in y. Not necessarily, it depends how much above, right? And so because of that, we say that the correlation here is equal to 0. That's why it's so important to remember that correlations only talk about linear association. If you have any other type of linear association, your R is not going to pick that up. I don't even know why I do something else. Okay, do I have a question or is this okay? All right, so based on that, now we can go to the formula. Oh, I think I left some space over here for the formula. Yes. So for the formula, we're going to have that R, the correlation coefficient, is going to be given by S xy divided by Sx times Sy. So a lot of notation, doesn't look that difficult. I'll explain what each one of them is, but you're gonna see you're usually given each one of these values regardless in each of the problems that we're going to be solving. So Sx is just the standard deviation of the first variable, so the variable that's in the x-axis. Standard deviation of the variable in x. Sy is the standard deviation of the variable in y. And Sxy is something that we call the covariance. Okay, so this is something that is not, so the covariance, we don't really use it that frequently. It's a tool that is used in advanced statistics and so on, but here we don't really use it that much. All that it is a way to express how x varies with respect to y, right? So it just measures how x varies with respect to y, but for the purposes of our class, we're only going to ever use it in evaluating the R, in evaluating the correlation coefficient. So here I'm just going to repeat that this is the correlation coefficient. Is this okay? Please raise your hand if you're good with this. All right. So now I'm going to just say what the interpretation of the correlation coefficient is going to be, and then we're going to have maybe like an 8-minute break, and then we'll come back, do a couple of examples, and that will be most of it. So the correlation coefficient, we're going to say if it's between 0 and 0.2, we're going to say that there's no relationship. There's no relation between the variables, or it's really, really weak. So it's really not significant. Then, if we have a value between 0.2 and 0.4, we're going to say that the association is very weak. Then, if we have 0.4 and between 0.4 and 0.6 for the correlation coefficient, this is going to mean that we have a strong association. No, sorry, no, not strong. Cross that. Moderate. Moderate association. Then between 0.6 and 0.8, we're going to say that there's a strong association. Whereas if we have something between 0.8 and 1, this is going to correspond to a very strong association. Does everybody understand this? What was that? Okay, so this is how to interpret it. And yeah, so here is the mandatory warning so that you don't make this mistake at any point, which is that correlation is not causation. Okay, so we're going to see a bunch of things in class that are going to be maybe correlated, but we can't necessarily conclude whether one of them causes the other or the other causes the one, right? So it's going to become really, really important to make that distinction. Okay, so 8 minutes. At 12:58, I expect you back. We're going to be doing an example and then just develop something new as well. And I think that's most of it. 8 minutes. Okay, so if we're going to sketch a scatter plot for this, what I need to look at is the different data points that I have. And for each one of them, the first coordinate is going to be given by the number of beers that the person drank. And the y coordinate is going to be given by the score that they had of the sobriety test. For example, for the first person, you'll have 5 beers and a score of 6. That gives a point here. Then we have 2 beers and a score of 9.25. So that means 1 and 9.25 is maybe around there. Then 9 beers and 4.75. So this person drank 9 beers and then had a score of 4.75. Then we had 8 beers and 7.5 as a score. So that's 8, this is 6, 7.5, which is maybe going to be around there. Then 3 and 9.75. So 3 and 9.75 is going to be around here. 7 and 6.5. So 7 beers and a score of 6.5 is going to be around here. Then 3 beers and a score of 7. Then 3 beers and a score of 7. Then 5 beers and 8.75. So that's 5 and 8.75 is going to be somewhere around here. 3 and 6. That's 3 and 6. 5 and 8.5 is going to be 5 and 8.5. Maybe here. Then 4 and 8.5. So that's 4 and 8.5 is going to be here. 6 and 7.75. 6 and 7.75. 6 and 7.75 is here. 5 and 8.25. Okay, you were getting the idea here. 7 and 7.5. 5 be here. Then 1 and 9.5. And 4 and 9. Okay. Can I see a show of hands for those of you who had gotten up to a point more or less like this? All right, good. Important things, in this case, I'm not going to be too picky about the title, but in general, if you had like an assignment or something like that, of course, you have to make sure that the title is on. You have to label your axes, especially here, because you have two variables, so we need to be very clear about which variable is on which axis, and you have to put the tick so that it's clear, you know, what the units are in each one. So that's for the scatter plot. The next thing that we're going to have to do is to compute the correlation coefficient. Calculate the correlation coefficient, which we know is of the form R is equal to SXY divided by SX times SY. Now, I gave you this formula, and I could give you the formula for the covariance, but I really don't care about whether you know that formula or not. I just care about you understanding how to understand standard deviations. So in this case, like in any other case, you're given the information that you need for the problem. So you have an average of 4.71 for X with a standard deviation of 2.20. Okay, so you know how to compute this average. You also could technically compute the standard deviation, but I might as well just give it to you. Then you have Y bar is equal to 7.80. So the average score was 7.80 with a standard deviation of 1.43. And then the only thing that you don't know how to find is the covariance, which is SXY. And this, for this case, was negative 1.84. Now, based on your scatter plot over here, it seems reasonable that we should expect there to be a more or less negative association between those, right? Because it looks like the more beers the individual has, the lower the score is going to be. The score is never really that bad, but it looks like, you know, the more beers, the lower their score is going to be. All right, so because this is a case, then we can try to use that information in order to evaluate the correlation coefficient. And we have that R is going to be equal to SXY, which is negative 1.84, divided by SX, which is 2.20, times SY, which is 1.43. And if you evaluate this, you're going to get negative 0.587. Okay, the SXY, already that's a formula that is not, that I'm not giving in this class. It's like the sum of each one of the observations minus the average in X times the difference between the observation and the average in Y divided by n minus 1. All of those have to be added. It's a whole thing. It's really the same kind of idea as for a standard deviation, but for both X and Y at the same time, but there's really no point in us studying in this class. So I'm always going to either give you SXY, so that means I'll either give you the covariance, or you'll have to compute it, but you'll have to compute it using Excel with one of the formulas. So you'll be able to compute it right away. Again? Okay. So if the correlation coefficient is negative 0.587, this means that we have a moderate correlation, so moderate association, that is also negative. So we have a moderate negative association. Okay, so moderate means, well, it's not that strong, and negative just means it's going down. I think this is, from your perspective, this is down, right? So moderate negative association, and that that's it. So we have a way to find the correlation and we have a way to determine the association. Also, we're going to use this. So let me just copy this one. Copy and there you go. So I'm going to, wow. Not that. Okay. So now that I have the value for R, which is my correlation coefficient, I'm going to use that value in order to compute the coefficient of determination. So what is the coefficient of determination? Which again is just like a number that we just have to evaluate by squaring R. So R squared, coefficient of determination, is equal to the correlation coefficient, little r squared, which for our case is negative 0.587. Everything inside a bracket, right? Because the whole point is that the coefficient of determination is going to be a positive number. So I need to make sure that I put the minus inside the bracket so that I also square that. And that's going to give me 0.345. Okay, so this is just by evaluating that number, plugging in the correlation coefficient into the value of R. And what this is telling me, and this is the important part, this is kind of like the whole point of finding that coefficient of determination, is that now we can say that 34.5, so only 34.5% of the variation in the value of Y, so in the scores, can be linked to the number of beers. To the number of beers. Right, which means that if you get a good grade in the sobriety test or a bad grade, only 34.5% of what explains it is going to be the number of beers that you have, which is, you know, somewhat significant, but it's really not that much, right? If you want a sobriety test, you would like it to be a little bit more indicative of how many, excuse me, how many.
Bad drivers.
What's up?
So really, we're just all really bad drivers.
You're just what?
Bad drivers.
Essentially, yeah. Okay, so does everybody understand? Everybody lower your hands. Okay. I have Gemma and Carl still with their hands up. Okay, now, do I have any questions about this? If so, if there's anything that isn't clear, please raise your hand. If not, I'm going to assume you understood everything. Going once, going twice. Sold. We're going to the next part. So, okay, we've talked about describing the association between two variables. We're talking about determining how much of the variation of one variable it can be explained by variation in the other variable. The next thing that we're going to do is we're going to say, okay, now we've said that there is an association. We can determine how strong the association is. We can determine how much of one variable can be explained by the other one. Well, if all of this is due to a given association, then why not figure out what that association is going to be, right? Is it possible for me to determine what the link between the two variables is going to be? So another way of saying that is, okay, if I have the values of X, can I more or less predict what the value of Y is going to be? If I knew how many beers somebody had drank can I make an informed guess about what the score is going to be on the sobriety test? So that's the next thing that we're going to do here. Earlier in the class, I asked you, if somebody has 1 year of education under their belt after high school, based on this data set, we have that they're going to be making about 35K per year, right? So this is going to be the prediction that I'm going to make. Okay, and that is a reasonable prediction because I have information for other people that also studied for 1.5 for 1 year after high school. I can also, for example, say, oh, well, what if somebody studies for 3 years? Then it looks like the salary that we should expect is about $51,000 per year. Then I can do the same thing for, I don't know, after studying 6 years, maybe the salary that I should expect is $61,000 a year. And I can do that for each one of the values for which I have information. All right, so I can guess more or less like this in each one of them. Now, the problem comes when I have a value for which I don't have data, right? So for example, here, what if I wanted to determine how much on average will a person make if they spent between 6 and 7 years in school? What if somebody spent 6.5 years in school? Well, I know that they're going to make some kind of value probably between these two values, but I would like a more or less precise estimate, right? If I can, then I would like to get that precise estimate. So the whole point of trying to determine the association is that because I know that the association is going to be linear, because I know that all that that I can do is to find linear correlations, then what I'm going to try to determine is what is the line that best describes this association, and can I find its equation? Right? So given that, can I find the line that best describes the association between these two variables? Can I see a show of hands for those of you who understand this? Okay, so this is what we're going to try to do. Okay, the question here is, can I find the equation for this line? For this line. Now, I know that the equation is going to be of the form y is equal to ax plus b because, well, this is a line, right? I said my association can only determine linear relations between variables, and so I know that the equation is going to be of the form ax plus b. So when I'm saying, can I find the equation for this line, what I'm actually saying is, can I find the values for a and b? Does everybody understand this? Can I see a show of hands for those of you who understand this? Okay, well, of course, if I'm asking this question, it's probably because the answer is yes, and the answer is yes. This line is called the line of best fit. And its parameters are A. So A is the slope. So it tells me for a change in 1 unit in X, what is the corresponding change in Y. And A is given by SXY divided by SX squared, where again, SXY is just the covariance between X and Y. Right? So the same definition as before. And B is equal to Y bar minus A times X bar. So this is called the slope, and this is called the y-intercept. So the line of best fit is the line whose equation is y is equal to ax plus b with these definitions of a and b. Oops. Oh, you get it. Okay, do I have any questions here? Is that okay? All right, so just for interpretation, then we're going to finish the example that we started just a second ago. For interpretation's sake, we're going to think about what it means for A to be given value. So a couple remarks. The first thing is that the point whose first coordinate is x bar and second coordinate is y bar is always on the line. On the line of best fit, which is often referred to also as regression line. Okay. X bar, Y bar is always on the line of best fit, which means, for example, in this case, maybe the average would be somewhere around here, and then the Y average would also be somewhere around there. So the line should pass through that point. The next thing is that the slope, A, corresponds to the increase in Y for a 1 unit change in X. So a 1 unit increase in X corresponds to an increase in Y of A units. Okay, A being this A. And the last thing is that B is the y-intercept, which means it's the point at which your line crosses the y-axis. So it's like the point over here. It is very often, it doesn't have a meaning. Okay, so very often it's not something that you can really interpret because you can't really, I don't know, like for example, if you're thinking about the number of education years, if you have, no, that actually makes sense. But if you have like, I don't know, you're trying to compare heights versus weights, then it doesn't make any sense to consider a person that has a height of 0 inches, right? So because of that, often the value that you're going to get for B is not going to be well interpreted. So it's the value that corresponds to the expected value in the cases where X is equal to 0, but it's often there's no meaning. I'll be right back.
Sorry, what's the EXP value?
Expected value. So what you would expect if X were equal to 0.
Oh, okay.
Yeah. Okay, do I have any questions? Can you please raise your hand once you're done writing? Okay, so now in the same example that we had before, okay, so the formula for sxy divided by s and 2x's. No, this is not s times x, it's s of x. So that means the standard deviation for the variable x, the whole number squared, which corresponds to the variance. Or so like this is just the standard deviation that you're given for the variable in terms of x, and then square that number. So that means the top is the covariance between x and y, and the denominator is the standard deviation of x, the whole thing squared. Is that okay, Olivia?
Yes, thank you.
Yeah, okay, good. So then for this problem, we're given some information, right? We already have the scatter plot. What we're going to do is now compute the line of best fit, and then try to sketch it to see if it actually fits our data. Okay, so here's what I have. Line of best fit. Find the line of best fit. Okay. So when we say find the line of best fit, that means that we're going to find the slope for the line of best fit, and we're going to find the y-intercept. So we're trying to find A. So to find A, we're going to have that A is going to be sxy, which is negative 1.84. And then we're going to divide this by sx squared. So that means sx, which is 2.20 squared. And if you evaluate this, you're going to have that this is equal to negative 0.38. Then you have B, which is equal to y bar 7.80 minus A times x bar, so minus 0.38 times x bar, which is 4.71. And if you evaluate that, you're going to get 9.63. So that means that your line over here is the line y, which is equal to ax plus b, that's minus 0.38 x plus b, which is 9.63. Does everybody understand this? Please raise your hand if you do. Okay, so if I sketch this, this line, I know it needs to pass through the point 4.71, 7.8. So that's 4.71 is going to be maybe here, and 7.8 is going to be somewhere around here. And I know that when x is equal to 0, the y-intercept is 9.63. So that means it's going to pass somewhere around here as well. And so my line of best fit looks something like, well, hopefully you get that. Please don't. I'm sorry about that. Okay, so we found that B was equal to 9.63. So my line has to go through 9.63 and 4.71 and 7.8. So that's 4.71 and 7.8 is going to be around here. And so that means that the line that I'm looking for.
I think you stopped screen sharing.
I stopped screen sharing? Okay. Thank you. There you go. All right, so is that where we were? All good? Okay. And then our line is going to pass through these 2 points. Right, which seems like a pretty good fit to what we have in the graph. Okay, does everybody understand this? All right, and so what I have is that if, so this tells me that for every extra beer that somebody drinks, you should expect a decrease of 0.38 in the score that they get in the sobriety test, right? So if you increase the number of beers by 1, beers by 1, then you should expect the score to decrease by 0.38 points. Okay, everybody please lower your hands and then only put them back up again once you're done writing. Okay, maybe 30 more seconds to finish writing this up. Please remember to raise your hand as soon as you're done writing. In the meantime, if you're done writing, you can start opening the correlations data set that was on Excel that you should have downloaded before class. If not, then you can just follow the instructions. They're going to be recorded, and then you can finish what I'm asking you to do at home on your own by following the video. All right, so I'm going to change screens now. What do we have? Correlations data set. Okay, so here I'm just going to show you how to use Excel in order to do the same thing that we've been doing today. But Excel is, of course, a lot more efficient at doing this. Right? So the thing that we need to remember is the formulas for things. So we know that R is going to be given by SXY divided by SXY divided by SX times SY. And we know that if we have a line of best fit, then we're going to have that A is going to be equal to SXY divided by SX, the standard deviation of X squared. And B is going to be equal to the mean for Y, which is Y, minus A times X. Okay, these are the things that we've talked about today. So what I'm going to do is to try to find all of those terms that I'm going to need. So that means I'm going to need the average for X and the standard deviation for X. I'm going to need the average for Y and the standard deviation for Y. And I'm going to need SXY, the variance for Y. Okay, and then I'll be able to evaluate the R score, not the R score, the correlation coefficient and A and B. Okay. So in this case, what I want to determine is whether there is a relationship between the weight of people and their heights. So can I say that the weights and the heights are going to be related? The first thing that I'm going to do in order to explore the relation is to select all of my data. Right? So for these two variables, I can select it like this, just drag down all the way to the bottom. I'm going to go back up and I'm going to insert. And here, remember, you had a cloud of points, a scatter, and you can click over there. So what this does is create a scatter plot for both of my variables. Now, you know that you can add different elements. You can add axis titles, for example, here, and say this is the height, which was my X, height in inches, and this is the weight in pounds. And you can also change the format of your axis here. So if you go right click and then format chart area or format axis area and so on, one of the options that you're going to have is in the axis options to change the minimum value that you have here. So I'm going to set my minimum to 60. What is this? Okay. Yes, can I put the data on Teams? Mac, I'll put the data on Teams, but for now I'm going to explain it here and then you can follow the instructions on your own. But yes, I'll put the data on Teams as soon as we're in class. So then we can put the minimum here at 60, for example, and we'll see that that will make the data a little bit easier to read. Okay, you could do the same thing here with the weight if you want. The next thing I'm going to do is compute the average for X. So I just have to say equal. So that's telling me compute something on this cell. And then you can select all of the data for which you want to compute the average. Right? So that's average of this and that, close the bracket, and we're going to enter. Another option is to realize that this is just A2 to A81. So that's the cell A2 to A81. So then in the next step, what I could do is say, find the STDEV, standard deviation, always .s because it's for the sample, of A2 colon A81. And then it's already selecting the same data as before, right? So now we have mean, standard deviation. We can do the same thing over here for Y. We have, this is equal to average B2 to B81. And this is going to be equal to the standard deviation of the sample from B2 to B81. If you understand what I've done so far, please raise your hand. I'm not seeing any hands going up. Okay. All right, do I have any questions? Okay, so for the covariance over here, it's really simple. Excel also has a function for this. You have to write equals, and then you have to write covar, and it appears over here. So covariance And then again, dot S. Okay, so dot S, open bracket, and then we're gonna have the first array. So the first set of info that you have, that's A2 to A81, comma, and then B2 to B81. Right, so it's selecting both of them. You can also select them with your mouse and click, drag all the way down, and then put a comma and select with your mouse and drag all the way down. And then press enter. So that's the covariance over there. That means that R is going to be equal to the covariance divided by, and in brackets, I'm going to put Sx times Sy over here. Okay, so I have a correlation of 0.644. Okay. Now this is the long way, but this is the way that allows me to remind you of all of these formulas that you already knew. There's a much easier way in Excel, as there always is, which is equal correl, and then A2 to A81 to B2 to B81. And you get exactly the same result. All right, so of course, this is the way that we're going to use in general, that you're going to use for your research project and so on. Instead of trying to evaluate each of the steps, you can just evaluate the correlation right away. Now, same thing for A and B. Instead of trying to apply the formulas that we have, we're going to put everything in our graph right away. So can everybody please lower your hands? Okay, and now, is there anybody that doesn't understand something of what we've been doing in Excel? Okay, and the next step is nice, it's just clicking. So here you have the dots, and what we're going to do at the next step is to try to put the linear relation over here. So we're going to right click on one of those dots, and we're going to go to add trend line. Okay, trend line, that just means like the line of best fit. This is what we're going to add. I'm going to click there, and then there's a bunch of options that appear on the right. Okay, these options are exponential, linear, logarithmic, polynomial, and so on, but we know that ours has to be linear, right? Because we know that our correlation can only pick up on linear trends. And what you can do now is just display the equation on the chart. And then you'll see the equation is going to appear. You can move it so that it's easier to read. Then you can click again on the line. So whatever you click on, that's what you're going to be given options for. Okay? And I'm also going to ask it to display the R squared. So this is also giving me the coefficient of determination. Okay, so that means I now have the line of best fit. I have the coefficient of association. So this tells me that, this is telling me that a 1-inch increase in height corresponds to about 5 pounds of an increase in the weight. And it tells me that about 41% of changes in weight can be associated with changes in height. The rest might just be variation that is attributed to other things. Okay, so that's, for example, the variation that you see between different people that have the same height. It's not because they have the same height that they necessarily have the same weight. Okay. Does everybody understand this? Can I see a show of hands for those of you who maybe don't understand something? All right. So what I want you to do is to try to reproduce exactly the same thing that we did here. You can use the formula for correlation, so this is perfectly fine. Here, this is how you find the line of best fit and the coefficient of determination. I've added an assignment, which is just, you know, again, a homework, but to make sure that you practice. So you should try to do the same thing for the following, like the other 3 data sets that you have over here. So that's income, housing, crickets, temperature, and US unemployment, male and female. The questions are written down in the assignment that I opened on Leah. I put the deadline for tonight, but you can hand it in anytime before Tuesday, but try to do it as soon as possible, just so that you make sure that you practice a little bit about this, think about it, and then you can move on to something else. Is that okay for everybody? If so, please raise your hand.
Do we answer all the questions on a new document?
You can just answer them on a Word document. Yeah.
Okay, yeah.
All right. So if that's all, then I'll see you Tuesday. The grading is moving along. You'll get it as soon as I'm done with it. All right. Bye-bye.